we're going to be discussing chain growth polymerization kinetics. So hopefully you remember that step growth polymerization reactions are totally different than chain growth polymerization reactions. In the step growth reaction, any A can react with any B, like any alcohol can react with any acid if we're talking about a polyesterification. For chain growth polymerizations, we have an initiation reaction and it has a rate law. We have a propagation reaction and it has a rate law. And we have a termination reaction and it has a rate law. So chain growth polymerization kinetics are quite a bit different than step growth because we have one reaction and one rate law. So in this case, we're going to have 3. In these slides, we're going to focus on the kinetics of free radical polymerization. And we're going to talk about initiation, propagation, and termination. In free radical polymerization, chain transfer and side reactions are also fairly common and may need to be considered. So we're not going to do that in this course, but after you have the fundamental understanding of how to handle initiation, propagation, and termination, with just reading the textbook or looking at examples online, you'll have no problem going back and adding in chain transfer if that's something you need to do in the future. We have 3 main goals. We want to obtain an expression for the rate of polymerization in terms of rate constants, concentration of monomer, initiator, anything that's easy to measure experimentally. What isn't as easy to measure experimentally is the concentration of free radicals. So we don't want that concentration in any of our expressions. And if we're doing this for cationic or anionic polymerizations, we don't want the cation concentration or the anion concentration. So whenever we derive an expression, we've got to get rid of the concentration of the active species. And we'll talk about how to do that in a few slides. We want to know an expression for the degree of conversion. So how is the monomer being converted into polymer? And an expression for the average degree of polymerization. We do that differently than we do with step growth, but it's pretty straightforward. For free radical polymerization, initiation is often done with a peroxide. The peroxide has an oxygen-oxygen bond. That oxygen-oxygen bond homolytically cleaves, forming a radical on each piece that remains. The radical is the activated initiator, and that's what initiates the reaction. So remember, the definition of initiation is getting the active site on the first monomer. So we have to activate the initiator, and then the initiator has to add the first monomer. So these 2 reactions are our initiation, are required for initiation. So the kinetics of initiation, we theoretically could have 2 rate laws for the 2 reactions that are going on, but one happens much slower than the other. So because the decomposition of the initiator is much slower than the addition of the first monomer, we really only have to focus on that slower rate because it's the rate determining step. Okay, the rate determining step. So that's the one we care about because once we activate the initiator, the first monomer adds like that. We don't have to really worry about it. So how are we going to monitor, or how are we going to define the rate of initiation? So by definition, the rate of initiation is the rate of increase of the radical on the first monomer. So that's why it's DM1 with a dot, right? That is representing the one-mer, the monomer, with an active site on it. And this is known to be proportional to the concentration of initiator. Another way to think about it is how we can define that rate of initiation as the rate of decrease of the initiator shown in that second rate law. And you have that -2 because it is decreasing, so we get a positive rate. But that 2 is because you form 2 radicals for one initiator. Okay. So an important consideration is not 100% of the radicals initiate monomers. So we put in a F. It's the efficiency or the fudge factor or however you want to think about it, but that F should be as close to 1 or 100% as possible because you want your initiator to initiate the polymerization, to initiate the first monomer. So F can be anywhere from 0.6 and up for a good initiator. And it's just important that because there are side reactions that happen with those initiators. In propagation, this is when the chain is actually growing. So when a monomer ends to the end of the chain and the active site moves to the end and keeps going for free radical polymerizations. So what's really important to remember, the same assumption we made in step growth polymerizations we're going to make in chain growth polymerizations, and that's that reactivity is independent of chain length. And again, it's an excellent assumption. So because reactivity is independent of chain length, we only need one rate law for propagation, because otherwise we'd need a rate law for every length of chain and it would be just a total mess. Okay, so what is the rate of polymerization? Right? Polymerization is the rate at which the chain grows, and that's the rate of propagation. They're one and the same thing. So by convention, we use lowercase rp when we're talking about propagation, and we use capital RP for the rate of polymerization. Termination is when the chain ends get deactivated or the active site dies. And free radical is a little more complicated than anionic or cationic because there's 2 termination mechanisms. Termination by combination, where the chain ends come together and they form a new bond from those 2 radicals, or termination by disproportionation, where the chain ends find each other and then they transfer a hydrogen atom between the 2 of them and they go off and on their way. So the average length of the chain doubles when we're talking about combination, but it stays the same for disproportionation. So 2 termination mechanisms. And all we need to do is add those rates together to get the overall reaction rate, the overall termination rate. We just sum up the rate of termination by combination and the termination by disproportionation. Okay, and we can simplify it by using KT as the sum of the 2 rate constants for the individual. We now have 3 rate laws. Now what do we do? The big issue is we don't know the concentration of the active sites. It's really, really difficult to measure experimentally. So what we're going to do is we're going to use another assumption. This assumption is called the steady state assumption. And we are going to assume the concentration of the active species, the free radicals in this case, but also with anions and also with cations. We're going to assume that concentration is not changing with time. The concentration is small, and essentially what that ends up meaning is every time we form a radical, we kill a radical. Form a radical, kill a radical. So that concentration of radicals doesn't change with time. That means the rate of initiation has to equal the rate of termination. Because if we form a radical through initiation, we have to kill a radical through termination. And so Ri is going to equal RT, and that's the steady state assumption. And because of that, we can get the concentration of radicals to drop out of these equations, and then we can do a bunch of different things with them. So when we set Ri equal to RT, the rate of initiation equals the rate of termination 4 free radical polymerizations, we can very quickly and simply solve for the radical concentration. And now we have it, the radical concentration is expressed in either constants or things that we know or can measure, meaning the initiator concentration. To derive an expression for the rate of polymerization, we need to remember that the rate of polymerization equals the rate of propagation. We get that expression, we plug in for the concentration of radicals that we just calculated using the steady state assumption, and we get the top expression in the gray box. Now, we have two things that change with time: the monomer concentration and the initiator concentration. If you look at the top equation in the turquoise box for minus di dt equals kd times the initiator concentration, that's exactly the same. It's a first order rate law. It's exactly the same as radioactive decay. So we already know how to solve that, and we'll do it again on the document camera. But we get an expression for the initiator concentration, and now we can plug that in for the initiator concentration, and we're able to group our variables into collections for this rate of polymerization. So inside our first set of large brackets are all our rate constants. Next, we have our monomer concentration and our initial initiator concentration to the 1/2 power. And then we have this exponential that's coming from that initiator, because initiator is consumed and its concentration decreases with time. So if we look at that equation, we can separate the variables and integrate that and get an expression for concentration as a function of time. If we look at the second set of brackets, we can very quickly see that if we increase the monomer concentration, we're going to increase the rate of polymerization. Hopefully that makes sense. Also, if we increase the initiator concentration, we increase the rate of polymerization. But what happens to the overall chain length if we keep increasing the initiator concentration? Now, let's look at those rate constants in the first set of brackets. So the FKD come from the initiator, and we could change the initiator and change the rate of polymerization. But if we look at the KP and KT, those are related directly to the monomer that is polymerizing. So the rate of polymerization is proportional to Kp over Kt to the 1/2. So if we can increase the rate constant for propagation, our polymerization goes faster. If we can decrease the rate constant for termination, our rate of polymerization goes faster, right? And we're going to look at all of these in a little bit more detail, and we're going to learn what the Trommsdorff effect is. Now let's look at the rate of polymerization as a function of monomer and initial initiator concentration to the 1/2 power. So this plot is showing you the rate of polymerization versus that monomer concentration times the initiator concentration to the 1/2 power. So this data is very linear, and you can see that that tells us that our assumptions were really good, because the data fits right on a straight line like we would expect. And as we increase that monomer concentration, we increase the rate of polymerization, or we increase the initiator concentration. Okay. Let's consider the free radical polymerization of ethylene. Ethylene is gas, and the rate constants have a pressure dependence, not only a temperature dependence when we're talking about gases. So for ethylene at 130 degrees centigrade and 1 bar of pressure, Kp over Kt to the 1/2 is 0.05. Do you think the polymerization is occurring very quickly? No, it's pretty slow, okay? Now, if we raise the temperature just slightly, but we raise the pressure substantially, up to 2,500 bar, we go from 0.05 up to 3. So a 2 order of magnitude increase in those rate constants and a dramatic increase in our overall polymerization rate. The Trommsdorff effect is really important to understand because it can cause your reaction to run out of control. So as your polymerization reaction proceeds, you're converting more and more monomer into polymer. And we all know that polymers are really big, really long. So as the monomer converts to polymer, the viscosity of our reaction mixture goes up, and it can go way up. And as that viscosity goes up, it becomes more and more difficult for polymer chains to diffuse past one another, in and through one another. It becomes very difficult for the chain ends to find one another. Why is it important that the chain ends can find one another in free radical polymerization? It's really important that the chain ends can find one another because that's how termination happens through combination and disproportionation. The chain ends need to find one another. So as the viscosity of the reaction mixture goes up, the diffusion of the polymers goes down, but the diffusion of the monomer doesn't really change because the monomers are tiny and they can diffuse in and around the polymer chains, no problem. So the rate of propagation doesn't change. The rate constant for propagation doesn't change. But what happens to the rate constant for termination as the viscosity goes up and diffusion slows down for the chains? Okay, so what happens to the rate of polymerization as KT gets small or even approaches 0? The rate of polymerization can race out of control, and if you're not careful, it can actually cause an explosion in your lab. So that's why the Trommsdorff effect is so important. The degree of conversion is the fraction of monomer that's been used or converted to polymer. It's pretty straightforward to calculate. The calculus isn't bad, the algebra is a little bit tricky, but when you go through all of this, you get the expression on the bottom of the page. This expression is so complicated, I don't have it doesn't give me any real insight, but we can take that expression and plot it, or plot real data and compare it to this expression and see what's happening over time. So here's a plot for conversion, the percent polymerization as a function of time. And if you look, the curves for 10%, 20%, and 40%, that is what that expression on our previous page, if we just plotted that, it would look like those three curves. And that 10%, 20, the percentage on these curves is related to the concentration of monomer in the reaction mixture. So 10% monomer, and then the rest is a solvent or something else, where 100% monomer means that you have nothing else but a monomer and initiator. Okay. So we can see at very high concentrations of monomer, we deviate very quickly from that conversion curve, the curve we expect. Any thoughts as to why? What were we just talking about? So, if we're deviating from our expected curve, it means that one of our assumptions is failing. So, what assumption do you think could be failing? Maybe the steady state assumption? maybe Ri no longer equals RT because termination has slowed due to the Trommsdorff effect. Okay, something to think about. And finally, let's just look at maximum conversion. If we go out to really long times, we never reach 100% conversion for this type of free radical polymerization. And that is related to the fact that the initiator is consumed. So if we wanted to convert 100% of our monomer, we would need to use not a peroxide initiator, or we would need to add more initiator into the reaction. So that's what this curve is showing us. Now, one thing we really want to know is what's the average chain length? What's the degree of polymerization? And specifically, the number average degree of polymerization is what we're going to be able to calculate. So with step growth, we used statistical methods and we included everything, right? But here in step growth, we don't want to include unreacted monomer because we're going to remove that. So this is a different mechanism than step growth, where everything went into the average to get the average chain length, because everything can react with everything else. Any A can react with any B. Here we have growing chains, dead chains, and monomer, and we want to exclude the monomer. So we're going to define something called the kinetic chain length. And it's defined as the rate of monomer addition to the growing chain divided by the rate at which the chains are started. That ends up just being the rate of propagation over the rate of initiation. And this is going to tell us the average number of monomers that are polymerized per chain radical, or per chain cation, or per chain anion at a particular instant of time during the polymerization. So the kinetic chain length, let's think about it a different way. If I've started 100 chains and I've polymerized 100,000 monomers, what's the number average degree of polymerization? The number average degree of polymerization is 1,000. And it's easy to think about it as how many monomers have reacted, how many chains are started. And if we want to put that in terms of kinetic quantities, we need the rate of monomer addition to the growing chains, the rate of propagation, over the rate at which we're starting the chains. And that's going to give us that kinetic chain length. The kinetic chain length, again, is RP over RI. We can take the given rate laws, plug them in, then use the steady state assumption to get rid of the active species. In this case, it's radicals. And then we get the expression on the bottom of the first box. And we can see that if we want to increase the chain length, we need to increase the monomer concentration. If we want to decrease the chain length, we need more initiator to make, we start more chains and still consume the same amount of monomer. We're going to have a shorter chains. Now let's think about free radical polymerization. We've got two termination mechanisms. We need to relate this kinetic chain length to degree of polymerization. If we terminate by disproportionation, the number average degree of polymerization is the kinetic chain length. But if we terminate by combination, two initiated chains now become one. So what happens to the kinetic chain length? It doubles, right? Okay, it doubles. So now the number average degree of polymerization equals 2 times the kinetic chain length. In almost every polymerization, we don't have 100% termination by disproportionation or 100% termination by combination. We're somewhere in between. And so we need to define a factor that's essentially the weighted average between these, that's gonna tell us how long our average chains are based on how much disproportionation and how much combination. And that expression is shown here. And that's that Greek letter that's hard to pronounce, C, something like that. I had a professor a long time ago who called it squiggle, and that is what I'm going to call it. So squiggle is just this collection of rate constants, and we can use that to get that number average degree of polymerization. Degree of polymerization is just 2 times the kinetic chain length divided by squiggle. It's always a really good idea to look at the limits and see if our derivation makes sense. So in a limit where the rate constant for termination by combination is much, much greater than the rate constant for termination by disproportionation, meaning that essentially we have 100% termination by combination, what happens? Well, if we look at the limit, we see it drops, the equation drops out as the number average degree of polymerization equals 2 times the kinetic chain length, which is what we want. And if we look in the other limit, where KTD, the rate constant for termination by disproportionation, is much, much greater than the rate constant for termination by combination, meaning that essentially we have 100% termination by disproportionation. Squiggle becomes 1/2, which gets rid of the 2, and so now our number average degree of polymerization equals the kinetic chain length as it should. Chain transfer simply changes the rate of dead chain formation. That information can be used to get a better estimate of the number average degree of polymerization when chain transfer is occurring, and that's usually what you want to know if you have a polymerization with a lot of chain transfer. You can refer to your textbook for more information. We won't be doing any problems that deal with chain transfer just due to time constraints in this class. So in summary, got to remember, rate laws are determined experimentally. They have to be verified experimentally. Assumptions are absolutely crucial to solving kinetics problems. If we don't make the right assumptions, these problems become intractable. We can't solve them readily at all. They become extraordinarily difficult. The 2 primary assumptions: reactivity is independent of chain length. That is true for both step growth and chain growth. The other assumption we've already talked about is the steady state assumption. That is only for chain growth, and the steady state assumption says that when we form an active site, we kill an active site, so that the active site, the concentration of the active site, is at steady state. That means its concentration doesn't change with time. That means Ri equals RT. And that is true for free radical, anionic, and cationic polymerizations. We can use kinetics to get concentration as a function of time, or extent of reaction as a function of time, and we can determine the average length and mass of our chains that are being formed. So we can do a lot with polymerization kinetics.